In section 8.2, we're going to talk about the union, intersection, and complement of events, along with odds of events as well. And here is the definition of what they call union and intersection. The takeaway from all this is that the union we have here is denoted by this symbol here with A union B, and the intersection is denoted by this symbol here for intersection. And essentially down here it kind of summarizes what it means. For A or B, we're taking the union. For A and B, we're taking the intersection. So the connection is for or is for union, and that's to joining the two together, A, B, putting them completely together. For intersection, A and B is what we're discussing, and that would be the part that they have in common with each other. So the picture here is meant to illustrate that the intersection is where they overlap, and the union is taking both events jointly together. On this example, where we're going to start is by looking at the single fair dice with 6 sides. That'll be our sample space. So 1, 2, 3, 4, 5, or 6 are the different numbers I could turn up on a single 6-sided dice. And we're going to start by looking at the probability of rolling a number that is odd and exactly divisible by 3. So let's start with the letter A, and let's let that stand for the event of rolling an odd number. And so the different numbers that fall for event A would be 1, 3, and 5. Those are the possible outcomes for event A. If we let event B stand for the event of rolling a number divisible by 3, then there are 2 numbers that would be in that event. Either a 3 or a 6 would be the 2 outcomes. So by our new notation where we say we're trying to figure out the probability of rolling odd and divisible by 3, that would be the same as A and B. That means A intersect B. So A intersect B is the situation of rolling an odd number and a number both divisible by 3. So for A intersect B, what are the possible outcomes for both odd and divisible by 3? If we look at the numbers above, there's only one that they have in common, and that is 3, both odd and divisible by 3. So there's only one possible outcome for the event of A and B. So the probability of A and B happening together, which is the probability of, in other words, A intersect B, is one outcome out of 6 possible outcomes, or 1/6. On the other hand, for part B, it says A or B. A or B means the notation of A union B. So in other words, A union B stands for the event of rolling an odd number or divisible by 3. So when we think about what possibilities work for this outcome, there are the outcomes of 1, 3, 5, and 6. These would be odd or divisible by 3. And so the probability of A or B, or in other words, the probability of A union B, would be equal to 4 possible outcomes out of the 6 total, 4 over 6, which is equal to 2/3. This is a definition of mutually exclusive. So for 2 events, if they're called A and B in this case, we can say they are mutually exclusive if they cannot happen at the same time. And in notation that we're using, that means the probability of A union B is equal to empty set. And that also leads us to a formula here that calculates the probability of the union of two events. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. So let's go back to the example of having two dice which are six-sided, or fair two six-sided dice, and talk about probabilities. In this case, we're going to start with what is the probability that the sum of the dice of 7 or 11 turns up. Okay, so let's start out by using the letter A to stand for the event where the sum of the two dice is 7. And let's let B be the event that the sum of 11 happens with the two dice. Then for A, we go through all the possibilities here, and 1, 6, 2, 5, 3, 4, 4, 3, 5 and 2, and 6 and 1 are all the possible outcomes where the two dice add up to 7. And for the event B, where they add up to 11, there are two outcomes in that event, possible of 5 and 6, and 6 and 5, and these would be the two that add up to 11. Now, what we can say is that these two events are mutually exclusive. And we can tell because they can't happen at the same time. By looking at the outcomes, there are no outcomes that they share in common. So they can't happen at the same time, and they're mutually exclusive. So what we can say is that the probability of A and B, or in other words, the probability of A intersect B, is equal to 0, since they can't happen at the same time. There are 0 outcomes where they both occur. So what does that help us do? Well, let's go up here to the number of outcomes. So again, we have 6 outcomes and 2 outcomes. And that'll help us do the probability where the sum is 7 or the sum is 11. Okay, and that'll be the same as the probability of A union B, which by our new formula is the probability of A plus the probability of B minus the probability of A intersect B. And since for A there are 6 outcomes out of a total of 36 possible for the dice, probability of A is 6 over 36. The probability of B, there are 2 possible outcomes out of 36. And like we said, for the probability of A intersect B, it's 0. So when we add these together, it would be 8 divided by 36, which reduces down to 2/9. And that's the probability of A union B. For part B of this question, we're going to have part A that says that this would be the event that dice are the same. And so the probability and the outcome, so the number of outcomes that for event the dice are the same, we'd have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. And let's let the event B stand for the dice add up to less than 5. And the possible outcomes for that event would be 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and 3, 1. And so now let's ask the question, are these mutually exclusive? Indeed, they are not. There are some of the outcomes that they share in common, namely the 1, 1, and they share in common the 2, 2. Those are both outcomes where the dice are the same and they add up to less than 5. So for the intersection where the dice are the same, and add to less than 5. That would stand for the outcomes of the 1, 1 and the 2, 2. So let's write down up here just so that we have for our probability calculation. There are a total up here of 6 outcomes for A and a total of 6 outcomes for B. And there's a total of 2 outcomes that they share in common for their intersection. So when we do the probability here, we're going to do the probability of that the dice are the same or add less than 5. That would be trying to take the probability of A union B, which is the probability of A plus the probability of B minus the probability of A intersect B. And since there are 6 outcomes for A out of 36, 6 divided by 36, same for B, minus for the intersection there are 2 outcomes out of 36. So minus 2 over 36. When we put this together, it'll be 10 divided by 36, which is reduced down to 5 over 18. And that's the probability on this one. The next thing to discuss is something called the complement of an event. The complement of an event, which is denoted with this notation here, let's say the event is E, they put a little apostrophe up above the E to represent the outcomes in the sample space that are not included in event E. As a result, the probability of E, the complement of E, is the probability of E not occurring. And this is calculated by the probability of the complement of E is equal to 1 minus the probability of E. And we see that on this next example here where it says the probability is 0.81 that a candidate wins the election. What is the probability that they lose? Well, in this case, the probability of losing would be the probability of not winning, which would be equal to 1 minus the probability of winning by the complement. So here that would be 1 minus 0.81 or 0.19. So in other words, how we write this in the notation is if we let E stand for the event of winning, then we denote E, sometimes called E prime, as the complement, or in other words, the not statement. So that means this E complement stands for not winning here. And as we see, the only thing we have to do to calculate the probability is to take the probability, subtract it from 1, and we get the probability of the complement. Let's take a look at this example here. It says an experiment consists of drawing 1 card from a standard 52 card deck. What is the probability of drawing a spade or a 10? Is what it says first. So let's look at this one first. Part A. Let's let D stand in for the event of drawing a spade. How many different outcomes are there for drawing a spade? Well, there are 13 possible outcomes out of the deck of 52 for drawing a spade. Let's let T stand for the outcome of drawing a 10. How many different 10s are there in the deck? Well, there are 4, so there are 4 possible here to draw from the deck. And what we're going to try to find here is the probability of both at the same time, or the probability of the intersection of D and T. So in other words, D intersect T is the event of drawing a spade and a 10. And how many different cards match that description? In fact, there's only one possible card out of the deck that matches the description of a spade and a 10. There's only one 10 of spades. So when we go about finding the probability of D or T, which in other words, probability of spade or a 10, which would be the union, D union T, that would be equal to the probability of D plus the probability of T minus the probability of D intersect T. And so the probability of D drawing a spade, there are 13 out of the 52, 13 over 52, plus the probability of a 10, which is 4 divided by 52, minus the probability of both at the same time, which there's only 1 out of 52. And so when we put all the numbers here together, it's going to equal to 16 over 52, which is equal to, reduced down to 4 over 13. Okay, let's look at this next one here that says, if D is the event that the card is drawn as a spade, and F is the event that the card is a face card, then we're going to find the probability of D union F. Okay, let's start off with F is a face card, is what F stands for. So the probability of F stands for the probability of a face card, which is one of the jacks, queens, or kings in the deck. So how this works is there are 3 cards of the face card varieties, jack, queen, king, of each suit. So there's for the suits of hearts, spades, diamonds, and clubs. So what that means is there are 3 times 4 equals 12 total face cards. And that's the total number of outcomes. So for the probability of a face card, there are 12 out of 52, or 12 divided by 52 for the probability. We already did the probability of a spade a second ago. There are 13 of those. So the probability of D is 13 divided by 52. Now the question is, there are 3 spades that are face cards. So that means that we can talk about the probability of a card which is a spade and a face card. That would be the same thing as the probability of D intersect F. And there are 3 divided by 52. So what that means is if we go about trying to find the probability of a spade or a face card, the union of the two, then that would be equal to the probability of D plus the probability of F minus the probability of D intersect F. And so we put our numbers together here. That would be 13 divided by 52 plus 12 divided by 52 minus 3 divided by 52. Those all go together to 22 divided by 52. So what does that number stand for? That's the probability of drawing a spade, or, because it's union, or a face card. For this next one, we're going to look at an event D as the event that the card drawn is a black card, and F being the event that the card drawn is an ace. Okay, so keep in mind as we go through, this is what D and F is going to stand for the different events. We're going to find the probability of D intersect F complement. So let's write down here what's going on here. So D stands for drawing a black card. F stands for drawing an ace. And F complement stands for drawing a card that's not an ace. So how we do this here is to consider that in the deck of 52, half of the cards are black and half of them are red. So that means that's a total of 26 cards that are black. Only 2 of those cards are aces. Those are the ace of spades and the ace of clubs. So when we talk about D intersect F complement, we're talking about the cards that are both black and not an ace. So what that means is there are 26 black cards minus the 2 aces, leaving us with just 24 possible left over that are black and not an ace. So when we talk about the probability of the intersection D intersect F complement that I was asking for, again, that's the probability of drawing a black card that is also and not an ace. And we just counted up those possibilities here. 24 of those out of 52. So 24 divided by 52 is the probability, and that reduces down to 6 over 13. On this one, it says a story carries 4 brands of DVD players, brand J, G, P, and S. From past records, the manager found that the relative frequency of brand choice among customers varied. Using the given probability values for each of the 4 brands, we're going to find the probability that a random customer will choose brand J or brand P. So we want to find the probability of somebody choosing J or P, which would be the same as the probability of J union P. So that would be equal to, by the formula, the probability of J plus the probability of P minus the probability of J union P. So keep in mind that the last one stands for the probability that somebody chooses the brand J and brand P. But in this case, we're considering that they're not going to choose both at the same time. So these are going to actually be exclusive events, mutually exclusive. So for brand J, we have the probability up there is 0.31. We'll add that with the probability of P, which we have up there is 0.23, minus 0. Again, since they don't occur at the same time, in other words, they're not buying both. And so all we have is just those 2 numbers added, and that gives us 0.54. That's the probability in this instance. All right, on this example, it says a pair of dice are rolled 1,000 times with the following frequency of outcomes. And as they record them here, they record the sum and the frequency, or how often it occurs. So they're adding up the 2 dice after they roll them. So how many times did the 2 dice add up to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12? Those are the sum of the 2 dice. And you can see below the frequency, or how many times that sum occurred. What we're going to do here is determine these, or use these frequencies to determine the empirical probabilities and the odds for the events below. Now I have the odds and empirical probability definitions above. Basically, empirical probability is the same as regular probabilities that we would do. We just take the number of times it occurred out of the number of trials ran and divide them, and that would give us the probability. The odds are also listed here. Odds are when we take the probability of E divided by the 1 minus probability of E, and that gives us the odds 4. The odds against is when we take the probability of the complement divided by the probability of E. So we'll use the formula for the odds here in just a second. So for the first part, where it says the sum is less than 5 or greater than 8. So if we look at our table above, less than 5, and if we add together the frequencies of how many of those occurred, 10 plus 30 plus 60 equals 100 times the sum was less than 5. And how I'm getting that is I'm adding together numbers for the sum of 2, 3, and 4, and the 10, 30, and 60 frequencies together. And similarly, for greater than 8, if you look at the frequencies for greater than 8, those would be the 120 plus the 90 plus the 40 plus the 20. So there were a total of 270 when you add those together, different dice rolls where the sum of the two dice was greater than 8. The probability, let's call it of A, which will stand for the probability of a sum less than 5. There were 100 of those out of the total of 1,000 trials ran. So 100 over 1,000 is the so-called empirical probability. And then for the probability of B, let's say that's the probability where the sum was greater than 8. So there were a total of 270 of those trials out of 1,000, or 270 divided by 1,000. Okay, and so, but on the other hand, since these events A and B can't occur at the same time, you can't have a sum which is both less than 5 and greater than 8, so they can't happen together. The probability of A and B, or in other words, the probability of A intersect B, is equal to 0. So that helps us then to determine the probability of the OR statement that it asks for. The probability of the sum is less than 5 or greater than 8. Probability of A or B, which would be the probability of A union with B, would be the probability of A plus the probability of B minus the probability of A intersect B. So we have those probabilities above. For the probability of A, that's 100 over 1,000 plus 270 divided by 1,000. And since they can't occur together, the probability of intersection is 0. And so when you put those numbers together, it adds up to 370 over 1,000, or reduced down to 37 over 100. It also, though, asks us not just for the probability, but for the odds of this happening. To do the odds for an event like this one, we take the probability of the event happening divided by the 1 minus the probability of the event, rolling a sum which is less than 5 or greater than 8. And so the probability we calculate by taking the 37 over 100 divided by 1 minus 37 over 100, which is equal to 37 over 100 divided by 63 over 100. And essentially, since those 100s are the same on top and bottom, you can cross them out and reduce this down to 37 over 63. For the next part, we're going to consider two events. In event A, which would be the event where the sum is even. And let's start out by adding those frequencies together. Double check which ones are where the sum is even. That's going to be where we have 2, 4, 6, 8, 10, and 12. So when we add those frequencies together, that'd be the 10 plus 60 plus 110 plus 170 plus 90 plus 20. It comes out to be a total of 460. Let's let another event B stand for the sum of the two dice is divisible by 5. And so what are the outcomes, are the frequencies for that? If you look at the sum is divisible by 5, that would be for the 5 and 10. So that's the only frequencies we have there, is to add together the 100 plus the 90. So a total of 190 times that event occurred in the 1,000 trials. But here's one thing to keep in mind. There is some overlap between these two. The overlap happens where it's both even and divisible by 5. So they overlap for the sum of the dice being equal to 10. And there are 90 times where that happened. So what we say is, for the event of A intersect B, which is the same as the event the sum is even and divisible by 5, there is a frequency of the 90. So that helps inform us about the probability now when we go to the next step. The next step is we're going to do the probability of A union B. So that would be the probability of A plus the probability of B minus the probability of A intersect B. So the probability of A, there were 460 of those out of 1,000, plus 190 divided by 1,000 minus 90 divided by 1,000. That adds up to 560 over 1,000, and that will reduce down to 14 over 25. And oftentimes we'll also use the decimal for the probability. The decimal for this is 0.56 as probability. So what does that stand for? That's the probability of A or B. So the probability, the sum is even, or, since it's the union, divisible by 5. Again, to do the odds, we take the probability of the event divided by 1 minus the probability of the event. So we go here 14 divided by 25 divided by 1 minus 14 divided by 25, which is 14 divided by 25 divided by 11 divided by 25. Again, you can cross out the same number, the 25 from top and bottom, and the odds, which are often represented only in the fraction, are 14 over 11, or 14 to 11 are the odds. Here what we're going to look at is some actual more data collected into a table, and this one says we're dealing with past driving records, and we're going to be dealing with empirical probabilities as a result. The probabilities are listed here as the decimals, and the outcomes basically from the different events occurring here. So for instance, it has accident, no accident, versus the miles driven per year being either less than 10,000 or between 10 and 15,000 or more than 15,000. And it gives us the totals and everything we need to do here. So they've already listed out the numbers in the table as decimals. So these are basically can be thought as the probabilities from the empirical standpoint here. Okay, so the first one we're going to take a look at is the probability for an event A, which will be the probability for driving less than 10,000 miles. And that's what this says here. We're going to find the probability that if somebody was selected at random, that they drive less than 10,000 miles or had an accident. Remember, key in on the word and or in a lot of these type of questions. If we look at the table for where we have where they drove less than 10,000 miles, it's this column there. And if we look at the part where it talks about had an accident, it's the first row in our table. And so the probability of A is the 0.15. That's the total up for less than 10,000 miles. And then we're going to talk about the probability of B, which would be the probability that someone had an accident in this data. And the probability of B is over here for the 0.50. So what's the probability, though, where they happen at the same time, or A intersect B? So the probability there would be where they overlap with each other. So they overlap here. Notice in the table, there's a point where they go together over each other. And that's the part where we have the probability of A intersect B. And that's just the number, simply 0.05. So what does that help us do? Well, it helps us now go to the next step where we find the probability of A union B. We're doing that because we want to find the probability of less than, that they drove less than 10,000 miles, or had an accident. And we're going to do that using our formula for A union B. Probability of A plus the probability of B minus the probability of A intersect B. So that would be the probability of A, which is 0.15, plus the probability of B, which is 0.50, minus the intersection probability of A intersect B, which is 0.05. Put that all together, and the answer is 0.60. That is the probability of less than 10,000 miles driven or an accident occurred. On this one, we're going to talk about if a driver in the city is selected at random, what is the probability that they drive 10,000 or more miles per year and had no accidents? So we're going to key in especially on that word "and" that we have here. Okay, so first off, let's talk about the 10,000 or more miles. Let's see where we get that from the data. The data for 10,000 or more miles are the two columns over here. So if A is the event, A can be thought of as 10,000 miles or more. And so then the other part is about no accidents. So let's look at the table for that part. And so that would be like event B, where there's no accidents. And so the question would be the probability of having 10,000 miles or more and no accidents. That would correspond to the probability of A and B, or in other words, the probability of A intersect B. So this is not an or statement, this is an and statement about the two events occurring. And the and is again where they overlap with each other. So the probability of A intersect B is the overlap probabilities between the two events. So if we add up where they overlap, the 0.15 plus the 0.25, we'll get the probability of A and B. And that comes out to be equal to 0.40. On this next one, it says a shipment of 40 inexpensive digital watches, including 10 that are defective, are sent to a department store. The receiving department selects 10 at random for testing and rejects the whole shipment if one or more in the sample are found defective. What is the probability that the shipment will be rejected? Okay, now this question is going to have to break down into how different things can be selected. And so the outcomes are going to be based off of how many ways we can select watches and defective or good watches. Okay, so part one here is to talk about how many ways there are to select 10 watches from 40. Okay, and so the number of ways we can do that is, we start off with 40 watches. That's going to be the first selection there, or first choice that's being made. And then the next step we have one less watch to choose from since one has already been chosen. So there's only going to be one choice for the second pick. And then there will be 38 next for the third choice in the selection, since there's now one less. And this is going to continue onward from the 37 be the fourth choice, the fifth choice, the sixth choice, the seventh, the eighth, the ninth, and the 10th. So this would be here the 10th and last final pick from the set of watches. Now, to get the number of ways this could happen, we multiply together each of these numbers. The 40 times the 39 times the 38, all the way down to the last one, which is 31. And this is the total number of ways of selecting the 10 from the 40. Okay, of selecting any 10 watches in particular. Now let's talk about how many ways, though, we could get 10 good watches, though, from the 40, because some of those watches are defective. So let's say talk about selecting 10 all good watches. Okay, so since 10 are defective, 10 out of 40, we can say that there are 30 good watches to choose from. If I go along a very similar pattern to the last one I did, to choose one first, there are 30 to choose from. Then there would be 29. Then there would be 28 left after I've already picked out 2 watches. And the pattern will go on from here all the way down. So from 30 to 29 to 28 to 27 to 26 to 25. That would be the 6th watch, the 7th, the 8th, the 9th, and finally the 10th chosen. Okay, so what we're about to do now is come up with a probability. The probability of selecting 10 good watches. We're going to call that the probability of E. So the probability of selecting 10 good watches is equal to the number of ways of selecting 10 good out of the total number of ways of choosing 10 out of the total of 40. And the way we did that is the calculation we have up above. 30 times 29 times 28 times 27 times 26 times 25 times 24 times 23 times 22 times 21, all divided by 40 times 39 times 38, all the way down. Multiply all these numbers, 35, 34, 33, 32, 31. So this is a lot of stuff to do. So let's take the calculator and let it have it do it for us. So I'll plug it in. But when I do this, and you're doing this on your own, make sure to put parentheses around the numbers that are being multiplied together on top and bottom. So take the whole top, put it in parentheses. Take the whole bottom, put it in parentheses. So let me show you what that looks like here. So that's the top part done, divided by, now I'm going to plug in the bottom part. Once you get all those numbers put in, close that up with a parenthesis, hit enter, and we should have our probability number now for it. Okay, so let's round that off here, and let's round it to 0.0354. Okay, what did we just find? Well, we found the probability of selecting, again, 10 good watches. The question, on the other hand, asks the question of what is the probability the shipment would be rejected? So let's go back up there real quick and verify what we're trying to do again. And we're going to reject the shipment if one or more of the samples are found to be defective. So that means what happens if we don't get all good watches? What if at least one of the watches was not good? So here what we're going to say is the probability that something else happens, the probability of at least choosing one bad watch, is basically the opposite of what we just did, or the complement of what we just did, E complement. So it's easy enough to do by just taking the probability we just found and subtracting it from 1. The probability of not getting all good watches is 1 minus the number, which is 0.9646 probability. Okay, this one looks a little bit long, but it's not too bad. Let's read through what it says. It says, in order to test a new drug for adverse reactions, the drug was administered to 1,000 test subjects with the following results. 80 reported only adverse reactions was a loss of appetite, 90 reported the only reaction was a loss of sleep, and 600 reported no adverse reactions at all. If this drug is released for general use, what is the empirical probability that a person using the drug will suffer from both a loss of appetite and, keyword, loss of sleep? So again, there were a total of 1,000 test subjects here. And so here's how we can do this here. If we take 1,000, subtracting away the 80 that only had a loss of appetite, and subtracting the 90 for those who only lost sleep, and we take away the 600 that had no reactions whatsoever, then what would be left over is equal to 230 that had both loss of sleep and loss of appetite. So here's an illustration of what we just did. We figured out what was left over here as 230 that had both a loss of sleep and a loss of appetite. So the idea here is then to find the probability based off of that, the probability that they lost sleep and appetite. We know how many there are from our calculation above, the 230 in other words. So out of the 1,230, 230 divided by 1,000 is the probability, which comes out to be a decimal of 0.23.